Hello everyone, and welcome to today's Learning on Graph and Geometry Reading Group, where we'll be met by Chaitanya, Simon, and Alexander, who present their new paper on Hitchhiker's Guide for Geometry Deep Learning. This paper is a clear overview of the field and will really allow you to learn a lot about what is being done in the literature in a very intuitive and nice way.
So what you see on the screen is the surface of a cell or a simulation of it. And it contains all these atomic systems, these molecules sort of dancing around and interacting with each other geometrically, right? And this is what gives rise to biology and disease and medicine and life. And this is roughly what this talk's motivated by: systems with geometric and relational structure. And these systems can come from biochemistry, of course, but they can also come from the physical world around us. So from material science and so on. And you can also zoom out and, these systems exist essentially all around us. This talk is a hitchhiker's guide to geometric graph neural networks. I'm Chaitanya Joshi, and we've done this work together with Alexandre Duval and Simon Mathis, who are presenting together with me, as well as Victor Schmidt, Santiago Mire, Francisco Maliors, Taco Cohen, Pietro Leo, Joshua Benjo, and Michael Bronstein. So the objective of this talk, right, is to trigger discussions and exchange. So we're happy to be interrupted, of course. And, the idea with this paper was really, not to, publish it somewhere, etc., but to serve as a guide for newcomers and to serve as a go-to starting point for this kind of field. We found it very useful, for instance, for getting collaborators to speak the same language as us when it comes to working on these models. So before I dive in, right, here's a very quick executive summary for those in the know. The objective here of this work is to include almost all the contextual material you need to understand the field. The inputs, which are, these atomic systems, molecules, or materials, and so on. The outputs, so what are the tasks that you can do with these kinds of models? What are the applications? And then everything in between, which is actually a lot, but essentially these geometric graph neural network layers. And we characterize them broadly according to invariant graph neural networks, which use scalar type features, Cartesian equivariant graph neural networks, which are using 3D vector type features, vectors from physics. And then spherical equivariant GNNs, which do a change of basis to the spherical coordinate system. And then lastly, an emerging line of work on unconstrained graph neural networks, which are not always strictly enforcing symmetries. And the idea is that hopefully, like, by the time you make your way through this guide, you have a deeper understanding of what are the turnable knobs where innovation may happen, or where, how you might understand the field or read new papers in this field and, get to grips with them. And we've tried to categorize these architectures in terms of 3 axes of expressivity, or theoretical capabilities of these architectures. The first one is the body order of the layer, which essentially means how many of your neighbors you use to compute some invariant scalar features at each layer for every node. The tensor order of these layers, which means, whether you're invariant or equivariant message passing, as well as if you're using higher order tensors, then that perhaps dictates the frequency of your features, or, how expressive these features are. And then lastly, depth, which is quite simple and which just covers, how many layers of message passing you do, how deep you propagate into the graph. So that's a very quick summary, right? I don't need to motivate now why we should care about these models too much. I'll be very quick. We should care because they're the core machine learning tool for 3D graphs today. So if you want to do any sort of property prediction, like screening things, for instance, on 3D graphs, you use geometric GNNs. they're also the kind of representation learning model within a lot of generative models. So for instance, for biomolecule design or materials design, these architectures are embedded within your generative framework. And then lastly, they're also a big part of MD simulation models, which are learning to sort of predict the next state of your atomic systems. So geometric GNNs are obviously quite exciting, and there've been a lot of recent success stories of these models. And we'll dive into some background on sort of how to build them in this talk. So the first step is to transition from normal GNNs to geometric GNNs. Again, I'll be very quick just because I know this is a specialized audience. So you know normal graphs, and you know that graphs have adjacencies and features. In our talk, we refer to features not as perhaps H, as you might be used to, but S, which means scalar type features in a normal graph. Scalars essentially from physics, and it'll be clear later why. So that's just something to keep in mind. And then you know that you can do message passing, and the more layers you stack, you build this computational tree. I think the mental intuition is that you can imagine that you have neural networks laid out along the graph structure, and you're learning how to propagate information, right? So then when we go geometric, right, now your graphs are embedded in Euclidean space. So every atom or every node could be an atom, which also has a 3D coordinate. I have my geometric graph, this molecule with me, and it's really a set of nodes and edges, but each node also exists in 3D. So now you also have a notion of coordinates with every node, and optionally you have vector type features or geometric features as well. In the figure, you only see one vector feature, this arrow, but in general, you could have a list of vector features as well, but it's just easier to visualize just one, right? And what really makes these geometric graphs quite special is physical symmetries. So these vector type features and coordinates, they actually transform with Euclidean transformations of your system. So for instance, right, like you could take your graph and you could rotate it in 3D space. And that would mean that your coordinates are rotating, right? And these vectors that are attached to each node are also rotating, right? And importantly, your scalar type features remain unchanged. Similarly, you could translate your geometric graph in 3D space again. Now, importantly here, only your coordinates change. Your vector features don't. And the reason for that is that the vector features are usually defined with respect to your current coordinate. So there's a small distinction between vector features and coordinates, but essentially you have these two types of physical symmetries acting on your geometric graphs. And so if you were to build a neural network for these geometric objects, right, you'd need to respect these symmetries, or you'd want to build physics into GNNs. You'd need to account for these physical symmetries, and it would look as follows. So you have your 3D system, and you have certain information about it, right? And I'm just listing out some of the things. You have the potential energy of your system, you have the atom types, you have the 3D coordinates. You could, since graphs are unordered, you could permute your system. And that would result in, for instance, your potential energy not changing, right? It's the same molecule, but your list of atoms changes, right? So your atom type list and your coordinate list are now permuted according to how you ordered your nodes, right? So that's the kind of discrete symmetry of normal graphs. And then you can also consider 3D symmetries, right, which we just talked about, like rotating these systems. And what that means now is that your atom types are not changing, right? So the atoms remain the same, but a rotation results in a rotation of the 3D coordinates. And essentially, if you now replaced atom types, coordinates, etc., with features, like latent features, your features within your neural network would also need to retain all these semantics, or you would at least presumably like your features to retain those semantics as well. And those are the building blocks of geometric GNNs. So your scalar features must be updated in an invariant manner, and your vector features must be updated in an equivariant manner. So in this case, it essentially means that for these vector features, they should commute as you rotate your system. And to do so, you'd basically enforce or suggest this to your geometric version of message passing. And you would, essentially ensure that these physical transformations are respected in your geometric message passing. And this is what this talk is about. So studying how these functions are actually defined. And hopefully that's been, somewhat of a bridge into kind of just setting the terminology and now diving into the actual pipeline. Happy to pause for questions if anybody has anything to say. And if not, then I'll quickly summarize the pipeline before I hand it off to some of the others. So, we have this diagram in our work, which essentially lays out like all the components. Like this, there's a lot here, but I promise that we dive into each of them in the paper. But essentially, what you do, right, is you're starting with a data set, and you actually don't start with geometric graphs. Usually, you start with just 3D coordinates of your system, so a point cloud. And what you need to do is you need to compute a graph. You need to construct a graph. And there could be various heuristics to do this. I think it's most common to just consider some radial neighborhood or k nearest neighbor. But you could also just connect everything to everything, and you get then graph transformers or transformers in that case. And then lastly, if you're dealing with systems like materials, right, you also need to incorporate these periodic boundary conditions, these kind of notion of your material being an infinite tile in space. And you need to incorporate this into the construction of your geometric graph. So once you have your point clouds and then you've built your graphs out of them, right? Before you can feed these graphs into neural nets, you need to convert their features into embeddings, some initial embeddings. And usually what people do is, you have these atoms, so you just take the atom type and you do an embedding lookup for it. And then I think like there are other heuristics that you can use. There are other kind of ways to featureize this as well. Which Alex's paper, I think, covers a lot of the details on as well. But the most basic is to just consider the atom type and embed it. And then for distances, for instance, like for every edge, you might, consider some radial basis function for your distance and so on. We've sort of attempted to describe a few of these as well in the paper. And then the most important part, once you have these embeddings, right, is to then update these embeddings with these graph neural network layers, these interaction blocks. They're called interaction blocks because they're essentially learning to borrow information from neighbors, and they're updating the features of each node or each atom. And this is mainly what the talk will be about, essentially building different types of layers, which may represent different inductive biases or different trade-offs in terms of, computation or in terms of, expressivity as well. And then lastly, right, like once you update these atomic features, you've learned how different entities are interacting with each other, then you can predict different types of things. So you have an output block, which could be predicting atom level forces. It could predict something global about your system. It could predict its energy and so on. And then there are various considerations here as well, which are actually kind of interest to discuss as well. So that was, I guess, a quick overview of these class of models. And I can now hand it off to Alexander to talk about to start talking about the interaction blocks, right, which are the most interesting part. And yeah, also happy to pause for questions, of course.
Waiting for the questions. Simon, do you want to go first to present the equivariant section if your plane comes soon?
Or I think it's all good.
Okay, nice.
I think the schedule works out really nicely. So please go ahead.
Cool. And do you want to share your screen, or how do you prefer it?
Yeah, probably I will share mine. It would be easier for yours.
Good.
Can you enable me to? Oh no,
should be able to now. There are a few questions I see.
Okay, nice. So you can address the question. I'll continue with the different geometric GNN families that we introduced during this paper. Do you want to answer the questions, Chantana, that you see in the chat before I start?
I think they're already answered in the chat, actually. Yeah.
Okay, cool. So invariant GNN families is, maybe the first one that's you saw in the literature, and maybe one of the easiest one to understand as well. So let's get into it. And the important thing to remember here is that we want to learn latent representations that capture the overall topology of the 3D atomic system, right? While respecting the physical symmetries. And this implies that we cannot use, the coordinates of the atoms directly as they are, using, the usual nonlinearities and MLPs in GNN algorithms, or otherwise it would break these symmetries. And the way invariant GNN will deal with this problem is that they update latent representations by scalarizing the local geometric information, which means that they're going to compute some scalar quantities that are informative of the general topology of the atomic system. And they're going to use these quantities in their message passing to update the representation of each node. As you can see, it corresponds to the green methods on this figure, the invariant models. So they all have tensor order 0, which means that they all have scalar embeddings. And the key design choice lies in the body order of the scalarization, meaning how do you compute these scalar quantities from the geometric structure? To use only distances between pairs of atoms, to use triplets of atoms to compute bond angles, or even quadruplets of atoms to compute dihedral angles. And these methods are going to use these quantities inside the message passing to update their representation. And this field is very nice. It follows, what you would logically think of. You first start with distance-based GNNs, and the most common name is maybe Schnedt, which, in 2018, proposed an approach that uses relative distances to scalarize the local geometry. So as you can see in the equation, you update the representation of a node using, a message computed base for every neighbor of I, the neighbors J. And this message will be just a continuous convolution of the representation of the neighbor, Sj, as well as the distance between the neighbor I and the neighbor, between the atom I and the neighbor J. And this distance information, if you think about it, it's quite representative of the geometry, right? It tells you how far atoms are from each other. So it's already quite good to construct a representation of the graph of the atomic system that includes this topological information. The issue that we have here is it can't distinguish between certain types of graph. There are some graphs that have the exact same set of atoms and the exact same set of distances, but which are not the same 3D atomic systems because the atoms are not located, with the same angles, torsion angles in 3D space. Therefore, Schnedt will receive exactly the same quantities, the set of input for these two graphs, and it won't be able to assign a different label to these two graphs. Well, they have, different properties. They're not the same in 3D space. And that's, how the field evolved from there. DimeNet, which came, a few years next, it uses distances and angles between triplets of atoms to update the representation. So it means that to update the representation of an atom, it looks at, of course, all of the neighbors of this atom to get a sense of the surrounding of I, but it also looks at the neighbors of J, okay, the neighbors of the neighbors to compute this angle ijk, which gives, further information about, the surrounding of this atom in space. And it's also a scalar quantities that you can use and process with any function inside your message passing. So it's going beyond distances. But here again, you can't distinguish between some graph. There are some atomic systems that share the same set of distances and angles, while they are, different, as you can see on the slides. So we need to go further and to increase even more the body order of scalarization. And that's what GEMNET does. GEMNET moves to higher body order terms, and in particular to torsion angles between quadruplets of atoms. So if you see, we're still trying to update the representation of the atom I, and we're going to do it using, the neighbors J, but also the neighbors K of J and the neighbors L of K to compute, these different angular quantities that are informative of the geometry of the molecule, the angle IGK, the angle LJK, but also these torsion angles between the two hyperplanes IJ and JK and LK, sorry. And as you notice with the equation becomes quite complex, right? You look at on the neighbors of I, you also look on the neighbors K of J and on the neighbors L of K. So it means that you have to pre-compute, all these scalar quantities that, represent this geometric information and that you can propagate. So GEMNET is a super cool, method. It achieved a wonderful performance on a variety of tasks. And we just want to clarify here a common misconception, that there is in the field, meaning that GEMNET, is often seen as a universal architecture. And it is in theory, meaning that in the paper, it formulates, that with a complete graph and a certain discretization scheme, you could assign, and represent any invariant function, meaning that you could assign a different label to any distinct graph. And this is the case for the theoretical version of GEMNET. And I think that, the authors have even said it, that the practical GEMNET architectures does not always use this complete graph and uses a specific discretization scheme that does not make it universal, although, it's still very expressive. So I guess that's from this discussion, the question of what body order do you need to uniquely identify every graph? I think it remains an open question for this field of invariant GNNs. So if I wrap it up here, we saw that invariant GNNs, they pre-compute scalar quantities to capture this geometric information. And this is both a blessing and a curse. It's a blessing because you can use any nonlinearities and any functions to update your representations. And it offers, great performance in many use cases. But also the accounting of this higher order tuples is expensive. You have to calculate, these torsion angles between every quadruplets of atoms. You also define, which geometric quantity you use. You define the angles, the distances, the torsion angles. So you don't learn, this geometric information. And lastly, you only tackle invariant tasks, except for maybe the forces that you can compute as the derivative of the energy. But it's an invariant model, right? So it does not produce equivariant representations, both locally and globally. So I guess, yeah, that's, the field of invariant GNNs. And it's been, it's been a blooming field, over the past few years. And I think now is the time to talk about equivariant GNNs, Simon.
Lovely. Alexander, can you keep showing the slides? And I'll just say kind of, on the next slide we see, and you go ahead.
Yeah, we'll do that.
Does that work? Lovely,
Yeah.
okay. And because I'm at the airport, if there is bad connection, please just interrupt me and I'll hand it over to Chaitanya to take my part instead. That being said, I have the pleasure to talk about equivariant GNNs briefly. And there's often quite a bit of confusion because there's a lot of math and equations that come in. And there's also a lot of jargon from various scientific disciplines that I think comes up when we talk about equivariant GNNs and how they're currently implemented. And I think that's mostly because many of the authors of these networks actually come from a background in physics or mathematics. And what we tried to do in the Hitchhiker's Guide was to make an attempt at introducing it with the least amount of jargon we need. Hopefully that worked reasonably well. And what I'm trying to do here in this next 10, 15 minutes or so is to give you an idea of the headline ideas. Why do we want to do equivariant GNNs? What could be the possible takeaways and benefits? And also what are the ideas kind of that are needed implementation-wise? But I will not go into the details because there are, it does require going through a couple of equations, but for that I refer you to the Hitchhiker's Guide. That disclaimer being said, let's first start thinking about why you would want to build equivariant GNNs in the first place. And for that, it pays off to think about the invariant GNNs and what they're good at and what they're not so good at. And so the idea, as Alexandra just said, with invariant GNNs is that we just make our life simple, ensure that we have invariant outputs by making sure that the inputs to our model are already invariant. So maybe there are distances, maybe they are angles, etc. But that means we need to make a choice at the beginning, and that choice is which invariant features do we actually want to present, and those are fixed prior to message passing. And in particular, the invariants we can build up do not change if we stack more layers, for example. And so it's harder, in a sense, to make our networks adaptive just by scaling the architecture. And also the other problem is that if we say, if you think about angles, that requires thinking about triplets of nodes. If you think about dihedral angles, that requires thinking about quadruplets of nodes, and so on. And so if you start thinking about higher order geometric information, so basically higher order, I just mean geometric information that requires the positions of many, many atoms, we need to consider, duplets, triplets, k tuples of different positions or atoms, and that scales combinatorially. So scales essentially very inefficiently and can be very expensive to compute. So we're looking for a way that allows us to kind of circumvent that, to have our invariants that are being built up as we do message passing, or the quantities we build up as we do message passing, scale kind of with the number of layers we do. So if we have more layers, we can build up more complex invariants. And also, we want to make sure that computing those invariants as we go, kind of as we put more layers into the network, doesn't scale combinatorially as it would if we want to compute complex invariants via, say, triplets or k tuples. And so that's the motivation of why someone might want to go around and build an equivariant GNN. And maybe one last motivation is if what we want to predict is an equivariant quantity, say we want to, for example, predict an orientation, that's also much easier if we keep equivariant information around, because if we destroy any sort of orientation information, it's obviously hard to kind of generate that from nothing. So that's the why of equivariant GNNs. And on the next slide, you can see a slightly more visual motivation for that. If you think back and try to think as a GNN, right? You would only have access to your local neighborhood. So you'd sit at, for example, this blue node, and you could look at your neighbors, and maybe you measure the angles to them, maybe you measure the distances. And this beautiful example from Christoph Schitt and the rest of the Payne papers, Payne authors, shows how if you sit at this local blue node and only know the angles and distances, you can actually not distinguish the left graph from the right graph. You could distinguish them if you were, looking globally at the graph, but because you only have information from a local neighborhood, so in this case, the one-hop neighborhood, their one-hop invariants are actually exactly the same. They differ, however, on the right-hand side, in their equivariant local information, so in the way these one-hop neighborhoods are oriented. And you can see that illustrated by these little vectors, one kind of pointing towards the left, whereas the other points to the right. And that's different from the left graph to the right graph. And so if you had access to this orientation information on top of just the invariant information of angles and distances, you could actually tell that they are different, even if you only have local information from a single one-hop neighborhood. So that shows kind of in an example why we might think that equivariant networks are more powerful if restricted to the same local neighborhoods. A second example is on the next slide, where we try to again show the same intuition, which is kind of beautifully presented by the Picasso problem, which I think was coined by Jeff Hinton. And the tagline here is that sometimes, even though we might be interested in an invariant quantity at the end, say the potential energy of a particular molecule in a particular configuration, making this invariant prediction sometimes is easier, or even may even require solving equivariant subtasks. And you can see it from this little image here. On the right-hand side, you can see little arrows, kind of how these components are oriented. If we want to make a prediction of whether, you know, that we're looking at a face, or whether we're looking at a happy face or a sad face, we might want to know how the different components of that face relate to each other, how they are oriented with respect to each other. So I think that's enough motivation and intuition. Let's actually look at what these equivariant networks look like. At the top, you see here just kind of very loosely stand for scalars, and scalars are objects. It's a term that comes from both physics and mathematics, and it just means it's an object that doesn't have an orientation. So an atom type, for example, whether it's a hydrogen or a nitrogen, would be something that doesn't carry any orientation information. So you can see invariant GNNs basically have a projection to scalars at the beginning, and then all of the message passing happens with scalar quantities, which is why I put this function f of S1 to Sn. We compute a couple of scalar quantities and do message passing. How does that look differently now in the equivariant case? Here I figuratively put, again, S's, and then V's with a little arrowhead over them, which stands for vectors, or in general, kind of more geometric information, and we'll see what that will look like in a moment. So equivariant GNNs essentially keep vectors around in the internal message passing. So as we do the message passing layers, there's vectors, or maybe different geometric quantities with different geometric meaning other than vectors, as we pass through the network. And then if we wanted to predict an invariant quantity at the end, the projection would come at the end of the network, as opposed to the beginning of the network for invariant GNNs. So this is on a very high level kind of what it looks like. And we've already seen that we now have scalar features, vector features, potentially other geometric features. So what we need to do when we build those models is we need to keep track of what feature has which type, essentially. So, and type here corresponds to how a feature transforms. So a scalar would be a feature that doesn't transform, so it's of scalar type. A vector would be a feature that transforms in this kind of with a simple rotation matrix. And then there's other things that might, you know, transform if the global coordinate system transforms with a rotation matrix R, then maybe that feature would transform with a rotation matrix that covers twice the angle, essentially in the same time. So essentially, there's different ways how you could transform. And the key idea is that if we want to build equivariant GNNs, what we need to do is we need to do accounting, and that's Dali's interpretation of accounting with geometric quantities. And so what we need to do when we build equivariant GNNs is we just need to keep very diligent track of what sort of things, objects, and what we call them in our Hitchhiker's Guide types, with the allusion to type theory, what types of things we pass through the network. And I want to briefly pause here because I just want to say that this is really actually quite simple idea, right? You just need to make sure very diligently and cleanly what type you have at which point in time. And so that's really the underlying idea of equivariant GNNs. And the complexity now comes in how do you define those types, what are different multiplication rules, etc., that actually are allowed. And kind of if you multiply something of type A and something of type B, what sort of output types you get. That's where all of the complexity in the maths comes in. But the fundamental idea of keeping track of what you have at which point in time and how it transforms is actually fairly simple. It's literally just accounting. And so that's kind of what I want to emphasize here. And if we now account for geometric objects, we need to think of a couple of rules. I already mentioned that type is what we will use to refer to how an object transforms under rotations and reflections. You could generalize this actually to other symmetry groups as well, but we are interested in the case of 3D atomistic systems in rotations and reflections in particular. So we are interested in how things transform under rotations or reflections, because those are the symmetries of 3D space. And you see a couple of types here: scalar, vector, pseudo vector, and we'll go through examples of those. We then also need to, if we know what type this is and what type that is, we need to know how we can add them, because that's an operation we often want to do, and what sort of output we get, what type is the output. And then we also need to be able to know how do we multiply them, and what sort of type do we get out when we multiply. And then non-linear operation just says how. So we do need to know how do we do and what sort of nonlinear operations we're allowed to do with these. So on the next slide, I'm showing a little example. Sorry, there's a little bit of an announcement in the background. But in the next example, is it too loud?
So good.
Or it's all good? Okay. Oh, the noise cancelling's working wonders. So in this example, I just wanted to start with the familiar types that most of us know, which is scalars and vectors. And if we were to build a scalar vector GNN, so something that only works with scalars and vectors, we would have two types of messages. We'd have a scalar message, which you can see at the top, mi, and then we'd have a vector message at the bottom, mi with an arrowhead on top. And those could essentially take in, if we look at the scalar message, we use again scalar projections of the various quantities. So how can we get different scalars from, well, if it's already a scalar, it stays a scalar. But if it's a vector, we could essentially take its norm or take its dot product with another vector, and that would then give us a scalar. And so those are different ways of obtaining essentially scalars from vectors. And those are the multiplication rules and the understanding of, if I take a vector and I dot multiply them, I get out a scalar. Now, if we have a vector message, we need to think of all the possible ways of kind of, if we wanted to write down the most general vector message that we could build, if we allow ourselves to use scalar and vector features, then we have to think of all the ways that we're allowed to combine scalars and vectors such that the output is a vector. And kind of in the equation, you just see this exercise carried out. Essentially, what we can do is we can scale different vectors according to an arbitrary scalar, or v, which here are essentially vector features at every node. Sorry, let me restart that. So we can have the vector features at every node that we might collect, or we might have vectors between nodes. So xij is the vector pointing from node I to node j, and we could scale those by various scalars. And those are essentially the only ways we can get a vector from a scalar and a vector. So this is hopefully fairly intuitive. And the next question that then arises, which is also on the next slide, if we know about scalars and vectors, are there any, is this everything? Does this capture all of the geometric information we might care about? Or are there other geometric types of information out there that may transform differently or may hold different information? And as it turns out, there are actually objects that transform differently. And a simple kind of way of building them is by just taking the outer products of various vectors that we have. So you can see a scalar, and then T1 here is a vector, and T2 is an outer product of two vectors, for example. And an outer product of two vectors actually transforms with two rotation matrices. And so we can see that it doesn't transform the same way as a vector and is therefore not a vector, it's a new type. And so we found a way of creating new types which transform differently. And so that means we can add them to our table of accounting and use them as we do message passing. And we call this particular type of tensors or objects that can be created with geometric information, Cartesian tensors. And the word tensor here is again something that comes with a lot of physics lingo. And tensor just means a type of object that carries orientation information or indices in a sense. And it looks like a matrix here at the bottom, but then we can of course batten and stack it, and then we can put them back to back. If we have multiple channels, you can see that indicated by kind of the fading into the distance. So there's multiple different indices that we need to keep track of as well if we build an Equivariant GNN, because we need to keep track of not only the channels, but also for a given type what its components are, and that's just illustrated here. And if we do this concatenation, then we also need to remember how to transform these particular objects. And you can see at the top here, the light kind of pink color is a scalar which transforms with the identity as you do a rotation. And the notation that you see here with this D of R just means the D is a German word for Darstellung, which is representation in English. And it says, how do we represent a rotation for this particular type of feature? So D0 means a type 0, which is a scalar feature. And what does a rotation look like for this particular feature? And for it would just be identity, because a scalar doesn't transform. D1 would be for vectors. So that would just be literally the rotation matrix itself. And then D2 would be a more complicated function. So this just shows that if we concatenate the features, we essentially get this block diagonal matrices that tell us how they transform. And on the next slide, what often happens in practical equivariant GNNs is that we don't use these Cartesian tensors. So I've introduced Cartesian tensor types now, and you might wonder if you've looked at some of the popular networks, those aren't really, those don't appear. And instead what appears is spherical harmonics and spherical tensors. And so I wanted to spend a little bit of time to say why that is and why spherical harmonics are kind of so special in this regard. And what you can see on this example is that you can take any Cartesian tensor and decompose it into a scalar component, an antisymmetric component, which transforms like a vector, and a symmetric component, which transforms like an L2 feature. And it'll become apparent what L2 means in a second. And this is really intimately connected to spherical tensors, which are essentially a basis. They're kind of like the fundamental Lego blocks that allow you to build any particular object, which is transforming according to the symmetries of reflections or rotations. So in a sense, the reason these spherical tensors are special is that they are what's called irreps in the literature, irreducible representations. And for us, intuitively, that means they are the Lego blocks that you can take any representation, like a Cartesian one, and decompose it. And because of that, because they're essentially these irreducible components, they make a lot of the math nice. And they also have the minimal amount of components, essentially, which makes them efficient, fairly efficient, essentially, to keep it in memory, which I think is one of the reasons why they're used a lot in literature. And on the next slide, I want to briefly say how these spherical tensors, which are the Lego blocks, the irreducible representations of the rotation and reflection group, relate to spherical harmonics. And I wanted to make this brief metaphor of the elephant, which is similar to spherical harmonics, and then lots of blind people kind of touching the elephant at different spots. And depending on which angle you look at it, which perspective you take, whether it's the tusk or the trunk or the tail of it, it looks to you like a different thing. Maybe it looks like a rope, or maybe it looks like a spear. But really, it's the same thing. And in the next slide, you can see this metaphor playing out for spherical harmonics. And I think this is one of the main reasons for confusion for newcomers in the field, that there are a lot of different perspectives on spherical harmonics. There's this perspective from calculus, which tells you, spherical harmonics are complete orthogonal basis of all functions on the sphere. So you can do essentially Fourier theory on a sphere. There's, you might look in a physics textbook about spherical harmonics. They tell you, they dictate the shapes of the orbitals of the hydrogen atom. You might look into kind of algebra textbooks and you see how spherical harmonics are related to to harmonic polynomials, which are eigenfunctions of the Laplace operator, subclass of symmetric polynomials. Or you look into representation theory, where you see that spherical harmonics are basis of irreducible representations. And so because they're so versatile, you find so many different perspectives. And if you Google, you might not find the one that helps you understand the most, or kind of is the most helpful in what you're trying to do. And so the one that I highlight here is the representation theory perspective, which I think for a lot of the at least current literature, the most useful perspective to look at them, or the most useful lens to look at spherical harmonics. And that's really that they allow you to get a basis of these Lego blocks that I said earlier, the Lego blocks that allow you to either take any type feature and decompose it into those Lego blocks, or build any kind of more complex feature from those Lego blocks by using the spherical harmonics. And luckily, there's fantastic libraries that are available for kind of dealing with these irreducible representations. And I saw the author of one of them, E3NN, is actually with us in the chat, Mario Geiger. So he's made building, he and some of the other people have made building equivariant GNNs much less of a pain because they've implemented all of the legal operations for multiplication and addition with those spherical tensors that allow you to parameterize those networks. So yeah, and on the next slide, you can see one of the early networks that was built based on irreducible tensors. So based on what we call spherical tensors because of the relation to spherical harmonics. And I don't want to go into details of the equations and of this model. The details are in our notation in the Hitchhiker's guide. But as a very last thing of this section, I just want to give you the key idea that had to be solved in order to build these networks. And on the next slide, you can see at least one of the key ideas that had to be solved. And that is, you need to parameterize the tensor product. And the tensor product essentially is how you multiply those different kind of spherical types. And there's a way, so if you do a tensor product of different irreducible tensors or spherical tensors, there are very specific rules for what you get out. And what you get out is actually a direct sum of, or what you get out is a tensor that you can decompose into a direct sum of, again, irreducible components. And the Clebsch-Gordon coefficients are telling you exactly the change of basis that you need to do in order to make this decomposition. And then there's clever tricks that people have found to sparsify the Clebsch-Gordon coefficients by rotating your tensors in a certain way, like the ESCN convolutions. And so how can you parameterize the tensor product? On the right-hand side, you can see a figure which we took from the E3NN documentation, and you can see kind of in this nice way that Mario found to visualize things. On the left-hand side, you see 5x0e, which means we've got 5 scalar features. And then you see 5x1e, which are 5 pseudo-vector features. And then on the other side, you can see 6x0e, which are 6 scalar features and, again, 4 pseudo-vector features. And so what are all the possible ways that we can get scalar features out? Well, a scalar times a scalar gives us a scalar. And so when you kind of trace the lines in that picture, you can see I put a little 30 on top to say because we've got 5 scalar on the left-hand side and 6 scalars on the right-hand side, we can get 30 scalars in total. And we can also get scalars from the 2 pseudo-vector channels, so the 1e and 1e, and we've got 5 pseudo-vectors on the left-hand side and on the right-hand side. And so that allows us to get 20 scalar features, and we can see kind of that vertex of the graph that goes to the bottom 0e, which is the output. And so if we ask for 15 scalar output features, that in total gives us 30 plus 20 scalars, which is 50, and then times 15 because we asked for 15 different channels of them. And so we find that if you calculate 50 times 15, that's, I think, 750. And so we get 750 weights for the scalar part. And if you do the analogous computation, you get all the possible weights for the pseudoscalar part. And so in total, this particular tensor product has 960 weights. And you've seen it written out in equations on the bottom left. And so the bottom line here of kind of this whole slide is that by knowing how different types connect together to give different output types, you can assign a weight for every path. And by that, you can parameterize those multiplication operations. And as the very last point on the equivariant section, I just wanted to say there's many more ways in which people make this more complex. On the next slide, you can see, for example, MACE, which is a very popular and very effective model built on equivariant GNN ideas. And one of the problems that it solves is it kind of makes the computation of higher body order interacting terms more efficient. And you can see many more details of this in our Hitchhiker's Guide. With that, I want to hand it over to you, back to you, I think, Alexandra, to talk about unconstrained GNNs and anything else we can take in the questions.
Thank you, Simon. Do you want to take some questions now, or if there are any in the audience?
Yeah, sure. If there's any kind of understanding-based questions, very welcome to put them now. If there's kind of any more tangential or discussion type questions, probably best to hold them off for the end of the discussion. And then very happy to, of course, have a discussion there.
I don't see any for now, so I'll continue with unconstrained GNNs, and maybe you can see in the chat if you want to answer some of them. So let's move now to the last family of geometric GNNs. We called it unconstrained GNNs, and I think it's the most recent of these families. And the underlying idea behind unconstrained GNNs is that we do not bake the symmetries into the model like invariant methods or equivariant methods do, but instead we're going to use like different strategies to enforce or just approximate these symmetries. Can be canonicalization functions, soft constraints, or local frames, but we regrouped inside this paradigm all these methods that decide not to enforce the symmetry directly into the model. And therefore, they lie, in our figure at the top here, because most of them, so it's not all of them, but some of them like finets, they use scalar features only, so tensor order 0, but they manage to incorporate, many body information, because as they don't restrict their functioning, they can incorporate, the topological and the geometric information from just higher order neighborhoods as you add more layers. And maybe we will add a bit of motivation here. So the underlying idea behind this kind of models is that you want to offer greater flexibility to the model and let him, traverse a more diverse optimization path. Why? Because if you apply, either invariant or equivariant methods, you're going to impose, the symmetries and some constraints on the model design. So for invariant methods, we just pre-compute scalar quantities and only process this as the geometric information. If you look at equivariant models, you restrict the set of operations you can apply on your direction, on your geometric information. Therefore, you regularize the model and you potentially, restrict and hinder its capacity to express all the intricacies of the data. Besides, the functioning of equivariant GNNs is quite complex. It's sometimes computationally expensive, and so is computing higher body order terms in invariant networks. So kind of for all these reasons, we want to have models that are not subject to the constraints or imposing symmetries and find maybe alternate ways to learn or approximate the symmetries. And we hope that it will make just the learning of the GNN smoother, in the sense that although you do not restrict it to the desirable set of functions, you hope that your model is going to learn it and learn it in a better optimization landscape. And that's the whole, purpose behind unconstrained GNNs. We'll see maybe one example of unconstrained GNNs that's called FANET. And the idea behind FANET is to outsource the equivariance to the data representation. So we'll deal with equivariance with this data preprocessing step, and then we'll have a model that can, be fully flexible and process, the relative positions between atoms using nonlinearities and MLPs. And this FANET model is based on the Frame-averaging paper by Puni. I don't know if he's here today, but it's a great paper, and I would advise to read it. And the gist behind FANET is this. So you have your inputs graph that you look at, where you have X, the 3D atom positions, and you're gonna apply PCA on X. So you're gonna compute the centroids of the positions. You're gonna compute the covariance matrix, so a 3x3 covariance matrix, and you're gonna eigendecompose it. And using the eigenvectors, you project your input graph and its positions into what we call the canonical space. And this canonical space, it is the same for every Euclidean transformations of your input graph. Because no matter what rotated version of the graph you saw as input, using PCA is going to end up with the same projected positions. And then you want to pass this canonical representation to FANET, which is unconstrained. The symmetries have been dealt with already, so you can use geometric information as you want and aggregate predictions to get the results. The main constraint here is that your canonical space is not unique. You would like to have only one representation of all this Euclidean transformation. But in fact, because of the sign ambiguity problem of PCA, where both like the positive and negative sign of the eigenvectors are a solution to the equation, you have 2, 4, or 8 frames. So 8 projected atomic system from this unique sample. And therefore, you have to get perfect equivariance as stipulated by frame averaging. You have to pass each of them, so each of this projected atomic system, into FANET and aggregate, or into your GNN, and aggregate the results to get equivariant energy predictions, for instance, or invariant energy predictions, or equivariant forces prediction. Additionally, applying a transformation to get the equivariance back. And the way because we have to compute and pass this data to the model 8 times, you want to maybe simplify that in order to be more computationally expensive, less computationally expensive. And the way to do it is through stochastic frame averaging. That's what we propose to do it. And the idea here is instead of computing the predictions for each of the frames, let's pick one at random among the 8 frames during training, and let's compute FANET or model prediction only on this projected frame. Therefore, you have a prediction, the energy of the forces, which will not be equivariant or invariant, not perfectly, because you don't aggregate the results over all of the frames. However, as it's during training, you can think of it as a kind of clever data augmentation techniques, especially except that instead of having to look at all the possible reflections and rotations of the input system, you have a small and complete set of frames that you have to learn the transformations from. And this set of frames is therefore the one obtained by the PCA. Therefore, it yields the real benefit of this method is that as you've dealt with the symmetries, or you plan to deal with in the preprocessing step by mapping all of the Euclidean transformation to this unique canonical representation, then you can have a very lightweight and simple model that processes the relative positions between atom I and atom J directly using nonlinear functions, two layers MLPs, thus universal approximators. And you can have a simple convolution to update the representation of an atom I between the representation of the neighbor and a filter that is learned based on this MLP of the directional information. And I think that is the strength of this kind of methods, is that you can have a very simple, very fast, and very expressive as well model, provided that you dealt with the symmetries beforehand. And Chaitanya and Simon, they proposed a very nice paper about geometric Westphal lemon test and how to assess, the expressive power of geometric GNNs. And in this paper, they propose, a data set or kind of some synthetic experiments that you could use to assess how expressive, your method is, how good is it at distinguishing between different graphs. And if you look at these two K-chains here, so which are different, based on the orientation of this left-hand side atom, you can see that with feinets and with this kind of flexible GNNs and constrained GNNs, you're able in one shot to have perfect accuracy at distinguishing them, because you'll be able to grasp, these relative positions, which is different directly. Well, if you look at methods like Mathis, to be able to distinguish between them as they're locally equivariant, you need to have the full picture of the graph to tell that they're different. So you need like the information from the right-hand side to be passed, to the left-hand side in the way to capture that the relative orientation is different. And that's, could be a strength of this line of methods. And we talked a lot about feinet here, but there's many new approaches that kind of propose ways to implicitly or just rigorously enforce the symmetries. If you take, one of the earliest, it's ForceNet by Hu et al. And they have, it's the most simple way to do this. It's what about data augmentation? Just add some Euclidean transformations of the inputs, add them to the data sets, and see if your model is able to learn, equivariant or invariant function on its own. Then you have methods that start from an equivariant architecture and relaxes a bit the constraints that are imposed, to keep track of this, of doing, this accounting of the features. And they claim, that it enables to get more expressive nonlinear transformations in your message passing. And then you have approaches which are a bit similar to feinet, that try to create, this canonical representation of every input data. Kaba and all, for instance, they propose to do it by learning a shallow equivariant network to perform the canonicalization. So instead of using PCA as we do in feinet, you can learn, and have a network that automatically finds this unique frame of reference that you're going to use for every Euclidean transformation. And that tries to preserve as much, the expressivity and the information that is contained in the original input. So there's a whole field here. One last, maybe a different category of unconstrained GNNs is local frames by Pozdniakov, who propose, to define a local coordinate system at each atom, and they compute an average predictions, not like from averaging, but just based on these local reference frames, where therefore they manage to achieve equivariance by defining at each atom this local coordinate systems that are therefore, invariant, equivariant, to the transformations. So I guess that's it for unconstrained GNNs. The overall intuition here is how can we tackle, maybe the interplay between the function space that a model can learn from, and the ease of optimization of the ML algorithms. And it's maybe a new and underexplored network, which is much closer to what, standard GNNs do. And maybe, there's some more things to be done here in how can we deal with the symmetries beforehand, and therefore allow afterwards to have fully flexible GNN models or any kind of models which don't have to deal with the symmetries, because in some cases, maybe it's better than enforcing them rigorously. And maybe, that's a question that the field should ask itself, in which case do we need perfectly equivariant architectures that propagates locally equivariant messages and that enforce, these constraints rigorously as an inductive bias in the architecture? And when can we, or should we move, maybe to some less restricted architectures that still deal with the symmetries in a way, either approximating them or enforcing them as a data processing step, but having, a very lightweight and simple functioning with all the nonlinearities you can use. And on that note, I'll leave Chaitanya speak about, the future directions of the field, which I maybe started to mention a bit.
Yeah, I mean, I think we've all been discussing the future directions in the chat already. It's been super fun interacting with everyone there as well. And I think we can even just open the floor to questions in the interest of time, right? And as you can see, like I think this slide is good enough to kind of anchor the discussions. We were mainly thinking about a few of these questions, right, in our research. So the first one, which Alex already touched on, is right, with the rise of these new unconstrained architectures, how much of the symmetry in physics should we bake in? When should we bake it in, right? Something else we were thinking about is just like, we think about these atomic systems as these static structures in 3D space, but they're not, right? Like they're constantly jiggling and moving. And maybe when we do coarse graining, when we do construction of geometric graphs, how do we retain dynamics, flexibility, and just modeling the system closer to reality? And the last one was, how do we scale up? How do we manage this marriage of data, architectures, and hardware? And how do we perhaps move towards foundation models for atomic systems? So we're happy to take any questions. And I think it would be nice to sort of have people chime in as well.
Thanks a lot for the presentation. I think it was very clear and went smoothly, like with three different presenters, all doing a great job. Like very nice slides, very nice overview of the talk, and I think it was quite noticeable by the audience, like that we surpassed like 100 live attendees at some point. So great job doing that.
Oh, thanks for tuning
Now
in.
we can, yeah. I really like the work in general, so it's good. I don't have any question on my side, so if anyone in the audience have a question, please raise your hand.
I think we've got one. Alvaro, you have a question.
Yes, hi, very nice talk. Thank you so much for the presentation. I did have a question regarding to the scalability and in particular, like the number of nodes that these GNNs are designed to handle. Like, is it in the order of 50 to 100, or could they handle, for example, thousands of nodes? And in particular, like if it's a very large graph, and so the distance of the graph is really large, like the diameter is really large, do you expect problems arising from like messages not passing through the entire network, and maybe that having an impact on performance?
Yeah, I think like, I think that these models, they can there's nothing preventing them from being trained on graphs with thousands of nodes or more. And, they're trained in mini batch. They're trained via mini batches, right? So many times you'd batch up your examples, and on aggregate, these examples would have over 1,000 nodes. I think there's like no such theoretical limit. I think it depends on how many GPUs you have and the scale of your data set as well, right? Like you should have, I would say, like order of thousands to tens of thousands of examples in general to get value out of these models, in my opinion. And yeah, what was the other thing that you were asking at the end?
Yeah, so it's basically like, what if for one, like there are two nodes that have at the minimum
Like long range
like,
interactions,
yeah,
right?
5 to 10 edges, yeah.
Yeah, I think that's a question that I think people are very interested in generally in graph learning as well, right? Because of course, like if you use a sparse graph, then you just suffer the cost of not being able to do long range propagation, right? Um, one approach is to just connect everything to everything and build graph transformers, right? Um, and that works, like that's been shown to work here as well for atomic systems as well. I think there are trade-offs that we've actually discussed in chat. And then the other approach is to perhaps build in hierarchical structure into your models. That's something I'm very interested in as well. So I think there are variants of these models that can be, implicitly hierarchical as well, and that that can often allow you to, propagate long-range information.
Thank you.
Yeah. Yeah, and Marius linked to this paper where they ran equivariant nets on some ungodly amount of GPUs, right? Yeah.
Amelie, you can go next.
Okay, so I have two questions. The first one is regarding E3 equivariance versus SE3 equivariance, because I noticed there's a lot of E3 equivariant architectures, and I think molecules really need SE3 equivariance because of chirality, right? And so I was just wondering, like, what is the cost you pay when you use an E3 architecture instead of an SE3 architecture? Like what are the problems that come up?
Does anyone else want to answer? I'm happy to as well.
Yeah, go ahead and I'll complete maybe a bit your answer.
Yeah, I mean, yeah, I think it's it's really important, right? Like chirality is really important for a lot of molecular systems. Maybe as machine learners, we love to benchmark stuff, and maybe in order to beat benchmarks using the E3 equivariant version of the network was already enough, so maybe people didn't kind of invest the time in adding a cross product to their network. But I think it's actually fairly simple to switch between the two. But if you use E3NN, I think that adding sort of using SE3 equivariance can often have a bit of a computational cost compared to E3 because you use fewer irreps. Yeah, so I think it's just machine learners maybe being lazy. I don't think there's a good reason for using E3 equivariance.
And then the other quick question I had was, are there any references that you guys can recommend on how to get equivariance with clever positional encodings?
Well, for geometric graphs, right? Like one of the big assumptions people make is that positions or positional encoding. So positions are already given to you. So I'm not sure how you would, the way I understand positional encodings on graphs is for non-geometric graphs, like you'd create some sort of feature to indicate the connection of graph structure. And I think a really good reference is by a friend of mine, Vijay Dwivedi, who worked on this paper called Positional and Structural Encodings in Graph Neural Networks, or the Graph GPS paper, which threw the kitchen sink of GNNs at the problem. I think those are good references for positional encodings.
And maybe to come back to this E3 versus SE3 question, I think you have to look at the use case that you have in front of you as well. In most of the cases for molecules, you want SE3 indeed. But for instance, data sets like OC20, where you have a catalyst or an adsorbate, like H2O that sits on a catalyst surface, there you want E3 equivariance because you cannot, reflect your system. The catalyst is always on top of the surface, given how it's modeled. And therefore, in that case, you may want to go for E3. So have a look at the use case also that you're facing. Curtis, do you want to go next?
Maybe one last
Hi,
point on
thank you
the.
for.
I just wanted to make one last point on the pseudo-scalar, scalar, pseudo-vector kind of chirality point. The paradoxical thing is often kind of if you use SE3 symmetry, right, you are symmetric under rotations but not reflections, which means you are distinguishing between one chirality and the other. So you're distinguishing between scalars and pseudo-scalars. If you're using E3 symmetry, you are putting them into one box, and you're choosing not to distinguish between scalars and pseudoscalars, and so you're losing the information. And that happens in our picture of accounting, right? If you add a scalar quantity and a pseudoscalar quantity, for example, if you take the vector product of two vectors and then you do a dot product with a third vector, that will give you a pseudoscalar, which corresponds to the signed volume. But then if you add that to, say, a dot product, now that quantity will be a sum of a scalar and a pseudoscalar. And if you now rotate, reflect your system, you'll have the sum being x minus y. While if you don't reflect it, you have the sum x plus y. And so it depends on whether you think global reflections essentially play a role, in which case you would choose to keep those two channels separate in your accounting. But again, it's really, accounting and whether you want to diligently keep them apart if they matter or not, if they don't matter. And that's really all that is to it in a sense. Sorry, Curtis, I interrupted you.
Oh,
please
yeah,
go ahead.
okay. Thank you so much for the presentation. I just had a question. Normally in deep learning, we get better results if we make our nets deeper. But in message passing and graph neural networks, I'm pretty sure if you make the net deeper, you average out all the information, and so it performs worse actually if you make it deeper. And so is a solution to just use residual connections, or what is there?
If you use a GCN without residual connections, without batch norm, and stack 100 layers, you over smooth the signal. But if you use any practical graph neural network, which uses all the best practices of deep learning, I can only say that I've personally trained pretty deep GNNs. So in my opinionated opinion, over smoothing is not a real problem for graph learning. And I think architectures like Graph GPS show you how to, get rid of this problem as well. Yeah.
Thank you. I'll check it out.
All right, that was very opinionated.
Can I add something to your answer?
Yeah.
Yes. In general, people confuse the fact that deeper networks do not improve the performance because there's over smoothing or over squashing, versus the fact that deeper networks don't improve the performance because the task that you're looking for is a task that is really done only at short distance, right? It's like, I don't know, you're having a CNN on an image, you want to detect only one object in the image, and that object measures 3 pixels. You don't need a 100-layer ResNet to be able to detect that. The thing is, with images is usually the useful pixels for your task cover a broad part of the image, and you need them to communicate with each other for the message to be meaningful. And here, when we work with GNNs, in fact, what we've noticed over the years is that we're able to build deep GNNs on some tasks, but not on other tasks. So, and it's basically because the task that is needed requires only short interactions. And from all the papers that were presented today, I think one of the most popular one is the Mathis paper. And it is famous for using only 3 layers. So why only 3 layers is enough for 2 layers? Oh, sorry, I was 50% off. So only 2 layers in Mathis. So what makes Mathis so special that it works in 2 layers? It's actually just the physics. The fact that atomic interactions usually happen in a short distance. They don't happen in a long distance. And there can be some interaction, long distance interactions between atoms, but they are very rare, depends on specific systems, and much weaker than the close interaction. So even if you are to perform even if your task can benefit from long distance interaction, only with 2 layers you can probably get 99% of the accuracy without the risk of overfitting.
Yeah, that makes a lot of sense, right? Yeah.
I guess it also depends on the data sets that you have also. If you have only very small data sets, having, you know, very deep architectures are going to be quite tricky to train, and therefore you may have problems. And I know that, you know, the Meta team that works on the Open Catalyst projects, so materials property prediction, they started with very shallow networks. And as you know, they had more data sets, and maybe they also, you know, learned some tricks to avoid oversmoothing and these kind of issues. They managed to go to deeper and deeper networks. So maybe we'll go there one day. But I guess for most of the tasks that we have now, maybe it's not useful to go that deep, because either you have very small molecular system or very small data sets. And it doesn't make sense to go deep for the sake of going deep in these cases, I guess.
Yeah.
Yeah, I actually saw that. I think like the neural nets are actually like comparable to DFT implementations or like algorithms. So it's actually pretty good. But I was just wondering, because yeah, I know Mace is only 2-layer message passing, but yeah.
And something that needs to be kept in mind as well is, for some applications, I think you may want very scalable and fast GNNs. Like if you would try to approximate a DFT and you want to screen, you know, millions of potential candidates, you're going to apply your model like millions of times to compute the properties of a model. So if you have, you know, a huge model that takes a lot of energy, of time to make a prediction, maybe it won't fit a use case as well. So I guess, you know, you also have this, do you want very accurate predictions, or do you also want just to screen the candidates and have a gist or have a sense of what's happening in the space of candidates that you look at?